All right, so I've been trying to give you guys hints of how you know like where to go with the problem. I don't know that the math is necessarily so hard. It's just trying to know like what you're gonna do with the math, how to set it up. So I tell you you have a zero point 0.1 molar solution of ammonia, and I say K equilibrium constant B, and they call it a B because ammonia is a base, is given. So again, until the end of class last time, K hadn't been given. We had been solving for K. We had enough equilibrium information that we could plug in for K. Now that K is given, it is a decent hint that you will have to let X equal something. So when K is actually given, most of the time you will have to let X equal something because you don't have enough information to solve on its own like we did before. So this 0.1 molar right here is an initial amount. So we know when we're given starting amounts or initial amounts and that we have a reaction, sometimes ice charts can be helpful because ice charts help organize all of our information. So we have ammonia in equilibrium with its ions, ammonium and hydroxide. So again, the first thing we do in these types of problems is we write out the reaction. Well, the reaction is already written for me, so I can go to the second step. The second step you will do is if it is at equilibrium, you will write an equilibrium expression. So let's go ahead and write an equilibrium expression for this reaction. So products divided by reactants and then raised to their respective coefficients. Now, I didn't put water in here. Why? It's a liquid. Great. We don't put liquids or solids in our equilibrium expression. I'll call this Kb because it's a base. Ammonia is a base. And now I actually have the value for K. So I'm going to write what this equals because it was given in the problem. This equals 1.8 times 10 to the negative fifth. I am not solving for K. I am given K. So if K is given, more than likely you're trying to find one of these guys. And in fact, this problem asks you to find all of the species at equilibrium. So here's my expression. That's like step 2. I'm going to rewrite out the reaction on this slide. Is that thunder? Did you hear it? It was totally thunder. You know you live in Southern California when you're like, thunder. Never hear it ever. Okay, so I'm setting up my ice chart. The E again is for equilibrium now. And I'm setting it up because I was given an initial value, an initial value for ammonia. And that initial value was 0.1 molar. And then I'm going to ignore water, right, because it's a liquid. And then we should not have any products initially. Now, in some of the other problems, except for the one we just did before this, I gave you additional info. I was like, hey, well, first of all, we didn't have K, but I was like, hey, the concentration of ammonium at equilibrium is 0.01. And then we worked our way backwards to figure out all the other guys at equilibrium. I don't have that now. Basically, I don't have enough information to keep going. And because of that, this is when you are forced mathematically to let X equal something. So I'm going to write out the words let X equal. Now, you pick a product. There is a strategy so that you don't have fractions. So we're going to pick a product, and we're going to pick a product that has a coefficient of 1. So in this case, it doesn't matter who you pick because they both are 1. It doesn't matter. Here's what I mean by this. If, let's pretend for just 1 second, I picked x in this circumstances, I would want to pick ammonium to be x. The reason that is because if this is x, this guy is going to be 2x. If I pick hydroxide to be x, this guy would be 1/2 x. I don't like fractions. It's not that you can't do it that way. It's just I personally don't like fractions, and so I'm going to avoid it at all costs with this strategy. Now, I don't have a 2 in front of there, so it doesn't matter. So who do you want x to be? Which product should we let it be? Hydroxide. Awesome. Hydroxide at equilibrium. So this allows us to fill in some information, maybe not with numbers right now, but at least with a variable. So in my E row, I will put an X here. Remember, the I row and the C row combine to make the E. Initial change lets you know what you have at equilibrium. So if I went from 0 to X, I must have gained X. X was produced, X amount. Well, this is a 1-to-1 ratio. Remember, your C is where your stoichiometry occurs, your C row. So if I gained X here, I gained X here. And this is also 1-to-1, but reactants lose concentration. So that's 0.100 minus X. 0 and X is X. And 0 and X is X. And now I sort of have equilibrium values. Kinda. I mean, I have a bunch of variables in here, but we're going to try to work that out. And so now that I have equilibrium numbers, I can plug into my equilibrium expression. So the ammonium at equilibrium is X. The hydroxide at equilibrium is X. The ammonia at equilibrium is 0.100 minus X. Okay, I'm going to simplify the top because X times X is X squared. Okay. Now, this is what helps us avoid using the quadratic. In terms of the AP test, you won't ever have to use the quadratic or on my test, which means what I'm about to do will always work. So we're going to make this assumption. We're going to assume that this X right here is much smaller than the number I'm subtracting it from. Okay. So if X is much smaller than 0.1, when you subtract it from 0.1, it probably won't change 0.1 very, very much. So let me give you a fake number. 0.0001, yeah, 0.0001. If you take 0.1 and you subtract 0.0001, you're going to get 0.09999, which is basically 0.1. So in essence, this assumption allows me to do this. I get to get rid of this minus X because we're making this assumption that it's so small compared to 0.1 that when you subtract it from 0.1, it goes away. Now here's where kids mess up. Why can't you just make the X squared 0 then if X is so small? I didn't say X was 0. I said X was just smaller than 0.1. I didn't claim it was 0. In fact, it's not going to be 0. So a lot of kids are saying if I say that it's 0 right there, well, I'm not saying that it's 0. I'm just saying it's smaller, so much smaller than 0.1 that it won't change the number of 0.1 by all that much. Okay? So you can't just all of a sudden off your X squared on the top. This helps me avoid the quadratic because now I can solve for X without using the quadratic, right? I multiply both sides by 0.1. To get the X squared by itself. That gets rid of this over down here, right? And then I need to square root. And the x comes out to be 0.00134. Okay. Now, didn't we just say that x was pretty small relative to 0.1? Is this number fairly small relative to the number of 0.1? Sure it is. This is 0.1, this is 0.001. That is quite a small number relative to 0.1. So this is a decent assumption. So then, well, what does this mean? Well, I just solved for x. Well, look, I know who x is. It's ammonium. So in essence, I know ammonium's concentration. Ammonium's concentration is x. So ammonium, oops, I keep doing that. Ammonium is 0.00134, and now you have to just put big capital M in yourself because you should understand that concentration means molarity. Unless we're working with pressures, then you'd likely be putting atmospheres in. And then who else was X? Well, the hydroxide was also X, right? So hydroxide is also 0.00134 molar. Now the ammonia is a little bit more work, right? Because it's 0.1 minus X. So it's 0.1 minus the 0.00134. And yes, it does change it slightly. Okay, but again, this is still pretty darn close to 0.1. 0.0987 is pretty close to 0.1. Meaning the ammonia didn't change by much, meaning it didn't ionize very well. Very little of it is in ion form, and the majority of it is intact form. And this is true of weak acids and weak bases. They don't ionize readily. That's why they are weak conductors of electricity. Now I'm going to take you on a tangent. You can do la 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 and tune me out if you want to, but this will be what we do next chapter. I already took you on this tangent once with pH, right? I'm just going to show you something. There's another equation instead of pH. It's called POH. And so let's flash back. If you remember when we learned our strong acids and our strong bases, which was like a really, really ancient long time ago, it was in the chapter 4, we said acids have hydrogen ions, and hydrogen ions determines the acidity, and then all of our strong bases had hydroxide ions, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, all of those, right? So POH is the measure of basicity of a system. Now, do not confuse the scale. The scale you have learned your entire life, like 0 to 7, anything below 7 is an acid, anything above 7 is a base, is the pH scale. It is not the POH scale. So let's talk real quick with the scale. You have 0, you have 7, and then we max out at 14. Anywhere above 7 is a base. Anything below 7 is an acid. I'm just foreshadowing what we will about to start next week. This is your pH scale, okay? Well, you also can find the basicity of a system, known as the POH, because OH means base as opposed to acid. And the reason this is happening is because ammonia is a base, okay? It produces hydroxide ions in solution, which are basic. So if we know our hydroxide ion concentration, we could find something called POH instead of pH. See, pH measures the H. pOH measures the OH. So you would just go like this. Opposite log. And then I have my hydroxide concentration, right? It's right here. So the pOH is 2.87. And then you go, whoa, that doesn't match my scale. Well, you're right, because this isn't the pOH scale. This is the pH scale. So there is one more equation that you will learn. Well, there's a lot more equations you will learn, but there's one more that you can do to convert pOH to pH, because we are very used to the pH scale and not the pOH scale. And it looks like this. pH and pOH will add up to 14. So if you know one of them, you can subtract it from 14 to find the other. So, right, you put 2.87 right here plus pH. So you would subtract 2.87 from both sides, and my pH would come out to be 11.1-ish. Oh, 11.1 is a base, right, in our pH scale? And that's because ammonia is a base. It's a weak base, but it's a base. The stuff I just did with the logs is not on your test on Monday. I'm just kind of foreshadowing because that's where these problems are going. Okay? Okay. We are skipping these and we are moving to a little bit of math, but heavily conceptual. We'll start off with, I'm trying to use math to prove the concept, and then it will lean into heavily conceptual. So the reaction quotient Q just means if you have a reaction and you don't know if you're at equilibrium, you solve for Q instead of K, because the only time you can solve for K is if you know you're at equilibrium. It's set up the same way though. It's still products divided by reactants raised to their coefficients. And then what you do is you just compare that value to the magnitude of K, meaning K is often given so you can compare the two results. Okay? You can only use K if you know for sure you're at equilibrium. It's called the equilibrium constant. Any other time you will use Q. Again, though, it's calculated the same way as K is calculated. There's no difference in how you calculate it. So here's an example. They'll give you a reaction. Look at the Haber process. We're going to see this like 17 million times today. I didn't balance it for you, so you're going to want to go ahead and balance it. Nitrogen and hydrogen producing ammonia at equilibrium. So I've got a 3 here and a 2 here. And I say, hey, here is the K. Look, there's a little C right here. It just means concentration. No worries. This is what it equals. The equilibrium value is 0.105 at this temperature. Suppose you have this much hydrogen, this much nitrogen, and this much ammonia at that same temperature. And the reason they have to be the same temperature is because if the reactions aren't at the same temperature, you're comparing apples to oranges. You can't compare them. Okay? That's why they gave you the same temperature for both examples. I do notice that I did not give you molarity, but if you have all of the moles and they're all in the same container, it's assumed that the volume is the same for all of them, so moles is okay to use in your equilibrium expression. Now they ask you, is the system at equilibrium? Well, the only way to know that is to solve for Q, because we don't know if the system is at equilibrium. So Q, meaning I don't know if I'm at equilibrium, it still equals products over reactants raised to their respective coefficients. The expression is identical to the equilibrium expression. Oop. So we just plug and chug all of those numbers that they gave us in there. I don't remember what, I gotta look. 2 for ammonia, 1 for nitrogen, and 2 for hydrogen. So 2 for ammonia, 1 for nitrogen, and 2 for, 2 for hydrogen. 2 squared is 4, 2 cubed is 8, 4 divided by 8 is 0.5. So given this set of circumstances, given this set of circumstances, this is what Q is. So are we at equilibrium? Nope. Why? Because the equilibrium constant was 0.105. Does this say 0.105? Nope, so you're not at equilibrium. So then the question becomes is, well, where are you if you're not at equilibrium? Well, what the reaction will do, if a reaction can go to equilibrium, it will do whatever it takes to maintain equilibrium. So if it's not at equilibrium, it will shift one direction or the other to re-establish the equilibrium. So right now my Q is greater than K because 0.5 is greater than 0.105. This was given in the problem, the K value. Well, what does that mean? Q is products over reactants, right? So if Q is too big right now, it's too large. Who do I have too much of? Products, right? A bigger Q is going to be associated with a bigger amount of products. I have too many products to be at equilibrium right now. So what will the reaction want to do? It will want to shift to the left or towards the reactants to reestablish equilibrium. And it will. It will do that until equilibrium is reestablished. It will do that until your reactants go up so high that the Q starts to get smaller and smaller and smaller until it reaches 0.105 and equilibrium is reestablished. This is what the rest of the slide says. That's just everything I just said to you is written on here in words. Now, when I say it shifts to the left, what does that mean? That means these guys need to increase in concentration, and this guy needs to drop in concentration to get the Q to decrease in value until it gets down and meets 0.105. So these guys will go up. You'll make more of them while these guys will drop down, or this guy, I guess. Okay. Now, I'm going to do another one. So at 448, the equilibrium constant for this reaction, H2 and I2 is 2HI, is 50.5. So I gave you K. Predict which direction, this wording right here, predict the direction your brain should think Q. Proceeds if we start with 2 times 10 to the negative 10th moles of HI, 1 times 10 to the negative 2nd, or 2 to the negative 10th, 10 to the negative 2, 1 times 10 to the negative 2 of H2, 3 times 10 to the negative 2 of I2. Now they're all in a 2-liter container. So this throws kids off because now I gave you the volume. Technically the brackets mean molarity, right? And molarity means moles per liter. But aren't they all in the same container type of liter? So they're all divided by 2 relative to one another. So really you don't have to use molarity. I'm going to use molarity. I would like you to try to do this using moles so I can prove to you that it comes out the same whether you use molarity or moles. Here's when you would not be able to do this. If they told you that HI was in a 3-liter container and the H2 was in a 3 or 4-liter container and the I2 was in a 2-liter container, they would all be different molarities with different volumes. Then you would have to solve for their molarities before you could plug in here. But because they're all in the same container and the container is the same size for all of them, the volume isn't necessary. But it will work either way. So again, we're going to solve for Q because we don't know if we're at equilibrium. Again, Q is solved for the same way. products over reactants raised to their respective coefficients. Now I'm going to use molarities. So I'm going to take 2 times 10 to the negative second moles and divide by 2 liters. That's my molarity. And then the H2 is 1 times 10 to the negative second divided by 2 liters. And the I2 is 3 times 10 to the negative 2 divided by 2 liters. And I solve for Q. Oop, I almost forgot. This first one has a 2 up here. Don't forget it. What does this one come out to be? Anyone have the number? Anybody have a number? It's definitely smaller than 50. I think, was it 1.33? Okay. 1.33. So I did molarity. If you did moles, you still got 1.33. That's why I was trying to tell you. If the volume is the same for all of them, moles, using moles is okay. Well, this is less than K because K's value, and given in the problem, is 50.5. So let's talk about what that means. So Q equals products over reactants. Right now, Q is too small. Q is much smaller. To be at equilibrium, I need to be at 50.5, and right now, given this scenario, I'm at 1.33. And that's because I have too many reactants. Too many reactants will give me a Q that's too small. I don't want too many reactants, so what am I going to have to do? I'm going to have to shift to the product side, or to the right, so that I can increase my products. So I need the HI concentration to go up, and I need the H2 and I2 concentration to decrease until this number can get big enough to reach 50.5, and then equilibrium is established. So shifting to the right would cause an increase in concentration of HI while a decrease in concentration of H2 and I2 until equilibrium is established. Okay. So I'm going to talk about Lechatelier, this concept of things you can do to shift the equilibrium in terms of Q in the beginning, and then I'm going to kind of move on and do it more conceptually, but the conceptual part is still the Q versus K, but we're just going to look at it conceptually, okay? So the 3 main things that we're going to do is we're going to mess with concentration and pressure and or volume, because volume directly meshes with pressure, and temperature. Those are the 3 things we're going to do in this lecture. Now, the whole point of this is you're taking a system that's at equilibrium. It's fine going back and forth, and we disturb it. We put a stress in or remove something. We add something, we take something away. So like it's going back and forth, mind its own business, and then we mess with it. We disturb it, and that will cause a shift in equilibrium. So the first thing we're going to mess with is concentration. Okay, so I have this reaction of NO and Br2 making 2NOBr. We're going to increase either of our reactants. I'll do the NO first. So let's look at this. If I increase NO, so this guy's at equilibrium, and then I increase the concentration of NO. Maybe I add more of it. I now have too much reactant, right? Because I put more in there. So what's the reaction going to want to do? Well, it's going to shift to the product so we can make more product and restore equilibrium. And then this guy will drop down, back down, and this guy will drop down. The same thing would be true if I added more Br2. So instead I increase the concentration of Br2. I add more of it. Well, now I, again, have too much reactant. It was at equilibrium, and now I put extra Br2 in there. Now there's too much Br2. Too much Br2, the reaction's going to want to shift the opposite direction to alleviate the stress. It needs to make more NOBr, and these guys need to drop to re-establish and restore equilibrium. Now, what happens if I increase the concentration of NOBr? I add more of it. Well, now I have too much product. It was at equilibrium, and now you put in extra product. It doesn't want extra product. It was fine the way it was. So the equilibrium will shift the opposite direction, where these guys will increase in concentration, and this guy will go back down a little bit to reestablish equilibrium. Okay, now, what if I take stuff out, like I lower its concentration? So let's say I lower the concentration of NO. I remove some of it. Well, that's not good. Now I don't have enough reactants. So what's my reaction going to want to do? Well, it's going to want to shift back that way to get some back. So this will need to go back up, and this will need to go down to reestablish the equilibrium. What if I decrease the concentration of NOBr? I remove some of it. Well, now I don't have enough product. I was like, this reaction was like minding its own business, and then I disturbed it. I took some NOBr out, and I don't have enough product, so the reaction will shift back that way to get some back. So this needs to go back up, while these will have to drop back down to reestablish equilibrium. So this concept of disturbing a system at equilibrium is called Lechatelier's principle. I'm going to prove this to you using Q and K really quickly, and then the rest of it will be mostly conceptual. However, you're still really doing Q and K, you're just doing it conceptually instead of mathematically, all right? So I have the Haber process again, and I have a system on the left that I tell you is at equilibrium. I say, hey, this is at equilibrium. This is what exists at equilibrium in this set of circumstances. So let's calculate its equilibrium constant since I'm telling you it's at equilibrium. So K equals products over reactants raised to their respective coefficients. Well, I have one ammonia, right? There's one of them. I have 1, 2, 3 hydrogens. And the hydrogen is cubed because there's a 3 in front of it. And I have 1 nitrogen. So 1 squared is 1, divided by 3 cubed is 27. So 1 divided by 27, I think I still have it in my calculator. So this guy's equilibrium value is 0.037. Well, that's very small. Small K means we favor the reactants. Look how many more reactants are in here at equilibrium than there are of products. Okay. Now, I'm going to disturb equilibrium by specifically adding more ammonia. I'm going to increase the concentration of ammonia in this system by adding more of it. I'm not touching the nitrogen or the hydrogen. Now they will be affected, but I'm not touching them. I'm just messing with ammonia. Conceptually, let's look at this. If I add more ammonia to the system, which way is the equilibrium going to want to shift? Right or left? I have too much ammonia, so I'm going to shift back this way. I'm going to need to make more of this, and I'm going to need this to drop because I need to reestablish equilibrium. So my first question, and this is a very hard concept to understand. I'm going to change the concentration of the entire system by adding more ammonia, right? When equilibrium is reestablished, is the equilibrium constant going to change? Yes or no? No. A new equilibrium is established, but the constant will not change. What is the only thing that changes the equilibrium constant? Temperature. And I'm going to prove that to you in a little bit. Okay? So let's add more ammonia to the system. So in this specific example, they added 5 more ammonias. So now that we are in equilibrium right here, we're calculating Q, right? Because we're not at equilibrium anymore. So I'll rewrite what my K was. So I've added 5 ammonias. So I'm going to calculate Q right now. So Q equals, there are now 6 total ammonias. Products divided by reactants. My nitrogen and my hydrogen remain unchanged right when I add the ammonia. So I still have 1 nitrogen and I still have 3 hydrogens. So this is Q because I'm not at equilibrium anymore. Why? Because I just disturbed it. I got Q equals 1.33. Oh, you're right. We aren't at equilibrium. I've just disturbed it. Why? These don't match. This was K. So, mathematically, Q is bigger than K. This should make sense. If I added more products to the system, I now have too many products. So if Q is greater than K, and I have too many products, I need to shift to the reactant side to make more reactants. So I can get this number to drop down until I reach back to 0.037. So the question becomes, am I going to have identical amounts in the first original equilibrium as I do in the last equilibrium? Will I have 1, 1, and 3 in my final equilibrium? Absolutely not. Did we add more stuff in there? Yes, so there's going to be more stuff at the end. But there's going to be more respective to one another, which is why the constant doesn't change. So look at this new equilibrium. So when I shifted back this way, I was able to produce some more reactants. So I originally had 1 ammonia and 3 hydrogens. I've now been able to produce 2 nitrogens and 6 hydrogens. So my reactants have increased. And then whereas I had 1 and then I added 5, so I had 6, back at equilibrium, the ammonia dropped back down because I shifted this way. So now I only have 4 ammonias. So 4 squared divided by 2 divided by 6 cubed, products divided by reactants raised to their coefficients. Oh, what do you get? Equilibrium is reestablished with new concentrations, but the same exact equilibrium constant. The equilibrium constant did not change with concentration. Yes, you have more stuff, but you have more stuff relative. You have more of everything, for that matter. So we're going to do another one, except for this time, we're going to remove some stuff. I will warn you, this one doesn't come out as beautiful as I had hoped, but I'll show you that it's still really, really close. The beginning K, the first beaker, and the third beaker. So I have this system that I say, hey, this is what I have at equilibrium. So K equals products. There are 11 ammonias divided by reactants. There are 4 nitrogens, and there are 12 hydrogens. So to solve for K, you do products divided by reactants raised to their coefficients. I've done this one already as well. And it comes out to be 0.0175. That's the equilibrium constant. Okay, so now I'm going to decrease the concentration of ammonia, or I'm going to remove some of it. Those terms mean the same thing. Removing ammonia means you're lowering the concentration of ammonia. So in this problem, I'm going to rip out 7 of them. I'm going to remove 7 of them. Okay, so now I'm no longer at equilibrium. So I'm going to solve for Q now, because I'm not at equilibrium. So Q equals, well, if I remove 7 ammonia, now I only have 4 ammonia, right? My nitrogens for now, right when I remove the ammonia, remain untouched, as well as the hydrogens. Point 0.0023. And the original equilibrium constant was 0.0175. Now, conceptually, if I remove some of this from the system, now I don't have enough. So the equilibrium should shift back this way to get some of it back. And it will do that by lowering these guys' concentrations for them combining to make this guy. All right? So again, this is Q less than K. I have too much reactants and not enough products given this situation. So I need to shift back to the products until 0.0023 gets up, increases until it's 0.015175 and equilibrium is established. So as I shift towards the products, my products go back up. So they started at 11. I took a bunch out. It dropped them down to 4. But then when I shifted back that way, I got some back, and then the nitrogen and the hydrogen had to drop in order for me to shift to the right or towards the products. So now back at equilibrium, I have K equals products over reactants raised to their respective coefficients. And now I do realize this time this doesn't come out. 0.0175, 0.0165. I realize they're not identical. However, they're only off by 0.001 if you look at it that way. Okay, I know they're not perfect, but basically equilibrium was reestablished by shifting back towards the product. So I did get some products back even though I initially removed them. And then my reactants had to drop down in order to allow me to get more products back. Whew. Okay, This is the last we will do with the math part of it. I'm now just going to swing into the conceptual part of it, though really that we're doing the conceptual part, we're still really comparing Q to K. I'm just doing it in words instead of in math. All right? So you can change concentration of a system by diluting it, right? Diluting it lowers concentration, always, okay? When you dilute something, you need to focus on your aqueous species because those will be the things affected by dilution. Gases will not be affected, solids will not be affected, liquids will not be affected. Dilutions will affect aqueous species only. So what you do for dilution is you focus on which side has the most aqueous species. So if this is my equilibrium, HF making H plus and F minus, the left side of the arrow has one aqueous species and the right side of the arrow has two. 1, 2. So during dilution, anything that's aqueous does get diluted. It's not like only one thing gets diluted. Everything that is aqueous gets diluted. The problem is the side you have more aqueous species on, it gets diluted more because there's more aqueous species on it. So that means this side is more heavily affected by a dilution because there's more aqueous things, meaning this guy drops more drastically in concentration than, let's say, this side. So the equilibrium will shift back that way to try to regain some of that concentration back. Okay? So we're going to do one more concentration practice and then we're going to move on to gases and pressure. So I have this reaction N2O4 in equilibrium with NO2, and we predict what will happen, and I know all the answers are up, but we're going to do this conceptually. If you add or increase the concentration of N2O4, now you have too much reactant, so the reaction will shift to the right or towards the products because we need to make more products so that my reactant can drop back down. When I do that, this goes up, increases in concentration, and this will drop back down a little bit. It won't ever drop back down to what its original value was, but it will drop back down. So what if I add NO2? Well, if I increase the concentration of my product, now I have too much product. So I have to shift back towards the reactants to decrease the stress and re-achieve equilibrium. So this will go up, and this will drop back down a little bit. What if I remove N2O4? What if I take this away? Well, now I don't have enough of it, right? So what am I going to want to do? I'm going to shift back over here to get some of it back. So this guy is going to have to decrease in concentration to allow me to make more of this. What if I remove NO2 or I decrease its concentration? Well, now I don't have enough product. So what's my reaction going to want to do? It's going to want to shift back that way to get some product back, which would require this to decrease in concentration so I can make more of this. So shift to the right or towards the products. Okay. Pressure or volume. So let's remember back in the gases chapter, a decrease in volume is an increase in pressure. And then vice versa, an increase in volume is a decrease in pressure. Messing with volume or pressure will only affect gases. So when they talk about changing volume or pressure, you are only focusing on the species that have a G next to them or are gases. You completely do not care about anybody else in the reaction in terms of pressure and Lechatelier. I'm not going to read this to you. I'm going to do a practice with you. Okay? But this tells you how everything will work based on how many moles of gas you have on each side of the equilibrium arrow. So I have the Haber process again. I have nitrogen reacting with hydrogen to make ammonia. I have 1 plus 3. I have 4 moles of reactants of gas. 1 plus 3 is 4. My products, I only have 2 moles of gas floating around. So if I take this container, and this is a piston right here that can move, and I push it down, right, because gases are compressible. If I push it down, I've decreased the volume. If I've decreased the volume, I have increased the pressure, right, because there's less space for them to move around in, so they hit the walls of the container more often. Well, the thing is, this side, if you increase pressure, will be affected more because there's more gas. The more gas molecules you have, the more pressure they exert. So the side with more moles of gas will have the stress on it if you increase the pressure. So now I have, think of it like too much pressure. And that will affect the side with more gas. So what will it want to do to alleviate that extra pressure? It will shift to the side with less moles of gas to alleviate the pressure. So we will make more ammonia. Do you remember back in the way beginning of this chapter when we started writing equilibrium expressions and I introduced the Haber process and I said they speed up this reaction 2 ways, and the first way was with a catalyst and the second way was they put it under high pressures. That is because when you shrink it, the reactants run into each other more and increase how quickly you get out ammonia. The faster you can make ammonia, the more cost effective it is, right? So they do this reaction with a catalyst because catalysts speed up reactions, but they also put it under high pressure, and that's because of Lechatellier's principle. This reaction will go faster and produce more ammonia if you put it under more pressure. Okay? So in this reaction, different reaction, I have 2 NOBr and I have Br2 making 2 NOBr. And I'm going to say that the volume of the system is decreased. So when they tell you volume decreases, I know that the pressure is going to increase and it's going to affect anything that is a gas. How many moles of gas are on the reactant side? 2 plus 1 is 3. How many moles of gas are on the product side? Just 2, right? 2 gas molecules. So if I increase pressure, the stress gets added to the side with more moles of gas. So I've increased this side more. Now, that's not to say that this side doesn't get stressed. It just doesn't get stressed as much as the other side. So if the majority of the stress is over here, I'm going to shift to the right to alleviate that stress and let this drop down a little bit and let this go up. Okay. Now, what if I increase the volume of the container? Well, what does that mean? Let's see. If volume increases, meaning the container gets bigger, there's less pressure, right? Because now there's more space for the gas molecules to move around in, and they probably don't run into the walls of the container as often if they're not as confined in a small space. So pressure goes down. Like I don't have enough pressure now. So again, there's 3 moles of gas over here, and there's 2 moles of gas over here. So if I lower pressure, now I don't have enough pressure. How am I going to get more pressure back? I'm going to shift towards the side with more moles. So not away from it. I need more pressure, so I'm going to shift to the side with more moles of gas to try to get my pressure back up and reestablish equilibrium. If you know how it goes one way, It has to go the opposite way for the opposite concept. It's not like you can decrease the volume and shift right and then increase the volume and shift right. It doesn't work that way. If you decrease one way, you increase the other way. Okay? So as long as you know how it goes one of the ways, it will do the opposite the other way. The only time that doesn't happen is right here. If you have the same number of moles of reactants of gas as you do of products, changing the pressure just doesn't do anything to the equilibrium. They say that there's no shift, just nothing happens. So like it doesn't disturb the equilibrium by messing with pressure if all of your gas molecules are the same on both sides of the reactant arrow. There would just be what's called no shift. It just like sits there and minds its own business even though you're messing with it. Okay. All right, last one. So we're going to flash back to thermochem, one of the harder chapters, right? So we need to remember what endothermic and exothermic mean. Remember, endothermic is a positive delta H, right? Heat goes into the reaction, whereas exothermic, we have heat exiting, leaving the reaction. So when we wrote thermochemical equations, we would do, I'm just going to do a generic reactants and we're doing equilibrium right now, so I'm doing equilibrium with products. And if it was endothermic, we had heat going in as a reactant to the reaction. Always, if it's endothermic, heat goes in. Whereas when it was exothermic, heat was exiting the system or being spit out, coming out, produced. Okay? So, having said that, we're going to work with this reaction. And in fact, this is one of the demonstrations I will be doing for you. So consider the reaction between this dinitrogen tetraoxide and nitrogen dioxide. I have it balanced for you. And I give you delta H. So first things first, a delta H of positive 58 means the reaction is endo or exo? Endo. Positive H values are endothermic processes. So I ask you to write the thermochemical equation above. That just means that you include the heat on the proper side of the equilibrium arrow. If it is endothermic, heat is going in. So the heat would be a reactant. So this is what my thermochemical equation looks like. And the reason that this matters is if we're going to do Lechatelier principle and put stresses on the system, knowing which way it shifts, you kind of need to know which side the heat is on, because that's going to tell you which way we're going to shift. Any questions on the thermochemical equation before I keep going? Oh, hold on. We're not there yet. Okay, so here's my equilibrium, and I actually have these tubes. I have them here. The dinitrogen tetraoxide is a colorless gas, whereas the nitrogen dioxide is this nasty, and it's actually poisonous, toxic brown gas, okay? And they're at equilibrium with one another. Now, when you first look at the tube, when I show it to you, obviously it's going to look brown, because if one gas is colorless and the other gas is brown, all you're going to be able to see is the brown, right? So I'm going to mess with heat right here. Now, I'm going to tell you right now, everything that I'm about to do is on this slide, but I'm going to do it to you showing, and then all of the words are written down for you to be able to reread when you want to, okay? So let's put back our heat in here, right? We said that the heat was a reactant. Okay? Now, let's say we increase the temperature. Notice this is different from all of the other parts of Lechatelier with pressure as well as with concentration, where I'm not messing with these guys. Okay? I'm only messing with heat. So I increase the temperature. I've added a stress wherever the heat is. In this specific scenario, heat is a reactant. So now I have too much stress. I've increased stress on the reactants by adding heat because heat is my reactant. So if I have too much stress on my reactant side, I will shift to the right to try to alleviate that stress. Well, what does shifting to the right mean? That means the nitrogen dioxide will increase in concentration, whereas the N2O4 will decrease in concentration. Now, the reason we're able to see this visually is because there's colors involved, right? In essence, if you increase the temperature, this tube, this is just a sealed off tube, will turn more brown or more colorless. Increasing the heat adds the stress to this side in this example, which causes the equilibrium to shift to the product side, meaning I'm making more product and my reactant is decreasing. So the brown or the tube will turn more, and you will see this. It will get darker and darker and darker when I put it in a hot water bath, and darker and darker and darker. And then I will take the tube out and I will put it in a cold water bath. In other words, if I decrease the temperature by putting it in a cold water bath, I've basically lowered this, right? So now I don't have enough heat. So which way am I going to want to shift? Left or back to the reactant side to try to get it back. Well, if I'm shifting to the left, this guy is dropping in concentration because it's making this guy. So my tube will turn more and more and more colorless. It's not really called white or clear, it's called colorless. And then I can literally take them out and just put them back and forth and back and forth, and they will shift back and forth forever unless I break my tube and all the stuff escapes out of it. I mean, these tubes have been around before I started teaching here. They'll be in equilibrium literally forever. Okay? So again, messing with heat, you can't memorize this because the heat is not always a reactant. Sometimes it's a product. You have to know what side the heat is on to understand which way the equilibrium will shift. So everything I just said is here. Everything I just said is here. And now we're going to do a different type of reaction. Oops, I'm going to skip this real quick. Oh, shoot. See, I didn't want that. Okay. Okay. I'm going to skip I'm going to go back. Hold on. All right. So next one. Nitrogen and hydrogen making ammonia. This is exothermic. How do I know? The heat is product. I gave it to you. I said it's exothermic. So now, in this instance, I'm going to remove heat. I'm going to cool this down. That means I'm lowering this side because this is where my heat is located. In this reaction, if I cool it down, the reaction will want to shift back this way to get it back. Meaning cooling the system produces more ammonia, and then these guys will drop in concentration. Now, the reverse of this is true, where if I add heat, that means I add a stress to where my heat is. Now there's too much stress on the product side, so I will shift back to the reactant side, and these guys will be made while this guy drops, so I can reestablish equilibrium. Okay. The hardest part of this is realizing why K only changes with temperature. And hopefully you kind of recognize that even though we messed with, we had the ones where we did the 3 beakers and we like added ammonia, removed ammonia, and new equilibrium was established. And yes, we had more concentrations of stuff, but we still had the same equilibrium constant. So messing with the concentration didn't change our equilibrium constant, okay? Equilibrium was reestablished with the same equilibrium constant, so they were in the same ratio to one another. Messing with temperature totally changes the equilibrium constant. So let's talk about why. Oops. So we have the dinitrogen tetraoxide and nitrogen dioxide, and we said it was endothermic. Now, remember, if it's endothermic, that means heat is right here. It's a reactant. So adding heat in this instance added a stress to the reactant side because that's where the heat was, shifting us to make more products. Notice I didn't mess with either of these. I only messed with heat. In the one with the 3 beakers, I messed with some of the substance. So like when I did those, I like added NO2, so there was more in there, which allowed me to make more of this, but this to drop back down. I'm not messing with those at all. They inadvertently get messed with when I mess with heat, but I can't possibly, if I added the NO2, I'd have extra NO2 in there to turn into this so they can change respective to one another. That doesn't happen when you mess with heat because you're not messing with this or this. It will shift it, yes, but I don't have additional of this being added or additional of this being added to let the ratio change respective to one another because all I'm messing with is heat. I'm not messing with any of the species in the reaction. So when my heat shifts to the right here, my products get bigger, so K gets bigger, right? Because K is products over reactants, so if products gets bigger, K gets bigger, which means the reverse is true. If I lower the heat, now I don't have enough, right? So I shift back to the reactants. If I shift back to the reactants get bigger, so reactants increase, and that means K gets smaller. You need to be careful. This is only true for this reaction. You can't memorize this, is what I'm saying, because heat is not always a reactant. It's also sometimes a product. That means the reverse of this would be true if heat was a product or exothermic. So let's look at what we just did right here. In this instance, I lowered the heat, and me lowering the heat shifted to the products. Well, if products get bigger, K would get bigger in this example. In this instance, I increased heat. So I had to shift to the reactants to alleviate that stress. So reactants got bigger, which means K would go smaller. Again, the only thing that changes K is temperature. Concentration doesn't change it, pressure doesn't change it, only temperature. Okay, I'm basically done. There's a couple small things we'll do, but this is the bulk of the chapter. 99.9% of the chapter is finished.